All right, so aloha and welcome to my talk about getting cozy with auditing on macOS. As Matt mentioned, my name is Patrick Wardle, and I've worked at a variety of acronymed places, including some government agencies. Currently, I'm the Chief Research Officer at a small startup called Digita Security. And very briefly, Digita Security, we're creating enterprise tools for the Mac. All right, so what are we going to be talking about today? So we're going to start with an overview of auditing on macOS. Now, I'll be the first to admit that talking about auditing might not seem like the most sexy or interesting topic. But the reality is it's actually very relevant and something important to talk about. So as we'll see, auditing is very useful for both malware analysis and forensics. And if you're interested in creating security tools, we'll show how you can utilize the auditing mechanisms built into the operating system to build some very powerful security tools. Also, if you are a hacker or if you are developing offensive cybersecurity capabilities, it's very important to know what type of auditing may be going on the system so that your tools, your exploits, your capabilities remain undetected. We'll then dive into a built-in auditing mechanism or subsystem called Open BSM. And we'll see that this is kind of the de facto auditing mechanism on Mac. We'll then don on our black hats and kind of take a more offensive turn to talk about some vulnerabilities in the auditing subsystem. So first we'll talk about a kernel panic, and then we'll end by talking about some more interesting bugs in the kernel, one being an information leak and the other being an exploitable heap overflow. So let's start by talking about auditing mechanisms on macOS. Now, first you might be wondering, what is auditing anyways? And this is a question I had when I began this research. And there's a great quote from Jonathan Levin. Jonathan is the author of the very popular macOS internal books, highly recommended if you're interested in iOS and macOS internals. And as he states in his book, he says, auditing enables the recording of events which may have security implications. Now, another question might be, what's the difference between logging and auditing? And this is, again, a very valid question. So logging can be thought of a way to kind of monitor any kind of activity. So you think, in your application, you add a print statement or a syslog statement, you can print some value of some variable, right? This doesn't necessarily have to have security implications. Auditing, as I mentioned, is generally going to be logging or recording actions that have security implications. Logging is also opt-in. So if your application doesn't have printf statements or syslog, it's not going to generate any logging. Auditing, on the other hand, is enabled by default and is usually implemented at the kernel level. So for example, say there's some auditing enabled that audits login or logout events or syslog system calls. Your application might not want to be audited, but it's going to get audited by the system regardless. Why auditing? Briefly mentioned, from a security point of view, it's a very important thing for an operating system to have. So it can be used very useful for helping to uncover or understand intrusions or even malware infections. So for example, as we'll see, when events such as a new process is started, a new file I/O activity, perhaps even a new network connection, these are all events that can be audited by the operating system. So obviously, if a piece of malware or a hacker gets into your system, these are all events that can be recorded and can then help potentially uncover that infection or intrusion. Now, more interesting to me, though, is using the audit subsystems to create security tools. So for example, and we'll talk about some other tools later, I wrote a simple utility that's able to generically detect ransomware on macOS. So all the tool does is look for the rapid creation of encrypted files by untrusted processes. This is basically something that ransomware does. So what the tool does is it taps into the auditing subsystem to get process notification events and also file I/O events. So the audit subsystem will now tell the tool whenever a new process is started and also whenever a new file is created or modified. So then all the tool has to do is examine that file to see if it's encrypted and then keep track of some files and also see what process is creating those encrypted files. And then it can generically detect all known ransomware on macOS. So again, a very powerful tool that's pretty easy to implement thanks again to the auditing subsystems. So what auditing mechanisms are available on macOS? Turns out there's quite a few, and we'll talk through all of these, kind of looking at the pros and cons of each, and also identifying any limitations of each of these auditing mechanisms. So we'll talk about FS events, kdebug events, dtrace, and finally Open BSM. So first up, we have FS events. FS stands for file system. Now, if you're familiar with Linux, these FS events are pretty much similar to Linux I-notifies subsystem. So as its name implies, FS events, you can use this auditing mechanism to monitor or audit for file I/O events. And you can do this in 3 easy steps. So the first thing you do is connect to /dev/fs events. This is a special device file on macOS. You then clone this file descriptor and specify what events are of interest to you. For example, file creations, file deletions, et cetera, et cetera. Then what you do is, in a while loop, you just read off this file handle, and the kernel will deliver file I/O events to you. So let's look briefly in code how we can implement something such as a simple file monitor. So again, you can see in the code at the very top, we call open, and we open this dev/fs events device file. We then specify or tell the kernel what file I/O events are of interest to us. And since we're writing a filemon utility, we basically tell it, hey, we're interested in everything. So we set fse_report to every single event. We then clone the file descriptor, and then at the very bottom, we enter a while loop just reading forever off this file handle. And again, as these file I/O events come in, the kernel will deliver them to user mode via that file. And since we're reading off those files, we can consume and parse those events. So at the bottom, for example, if I touch a file and then remove that file, running this code, the filemon utility, we can see it detects the touch event and also the remove event. So again, pretty easy to write a fairly fully featured filemon utility using the FS events auditing mechanism. The next auditing mechanism I want to talk about is the kdebug utility. This is a built-in kernel trace auditing capability. Now, unlike FS events, which are limited just to file system events, the kdebug events pretty much trace all activity on the system. And Apple actually uses kdebug events in a variety of their own tools. So they have a latency tool, they have another tool called sc_usage, which shows system calls, and then they actually have a filemon utility called fs_usage that's built into macOS. Now it's interesting that they don't use the FS events auditing mechanism. They instead decided to use the kdebug. And this is because the kdebug mechanism is so much more powerful. So what happens is kdebug events are generated when code in the kernel calls a macro such as kernel_debug_constant. So on the slide, for example, we can see the syscall handler. This is the interface in the kernel where user mode code that is making system calls will go through and enter the kernel. And we can see in the code there's a call to the kernel-debug-constant macro, and this will generate a kdebug event. So if we're reading these events in user mode, we will get an event that a syscall has occurred. So programmatically, how does one subscribe to these kdebug events to get these audit notifications? So the first thing we have to do is we have to tell the kernel to enable this audit mechanism. And you do that via a syscontrol, and you pass in the kd-enable value. And then once it is enabled, you basically read events by, again, invoking syscontrol, this time with the kern_kd-readtr value. And this will then deliver to you these kdebug messages from kernel mode to user mode. Now, these messages are compressed and encoded, as Jonathan notes. But what we can do is we can consult the trace.codes file, which is a file that is in macOS. And this allows us to decode the events. So again, Jonathan has created an open source utility called KDV. And so this code, for example, is from his utility. So if we compile and run that utility, we can see a ton of events. I mean, this is just going to, fill the screen with all sorts of events. So for example, we can see events related to the CPU utilization, mock events, et cetera, et cetera. Next up, we have dtrace. Dtrace is a cross-platform auditing mechanism that is also available on macOS. And until recently, it was the de facto tracing mechanism. So in a nutshell, what you do is you talk to a dtrace driver, and you either do this through an API or through dtrace scripts, which are written in the D programming library language, which is why it's called dtrace. And basically, you specify to the kernel what probes or events are of interest to you. And there's thousands of these probes that you can turn on. There's ones for processes, mock traps, syscall, memory notifications. So on the table, we can see some of the dtrace providers. And again, these providers basically, you can think of them as high-level classes which the probes are kind of associated with. So here's an example of using dtrace. This is actually a dtrace script that ships with macOS, and it's called exec snoop. And what it's designed to do is basically allow you, from user mode, to observe process creation and exit. So basically, it's a process monitor. Unfortunately, though, on recent versions of macOS, dtrace is neutered by Apple's System Integrity Protection, or SIP. Basically, Apple says, OK, dtrace is awesome, but we think it's a little too powerful for the everyday user, so we are going to disable it. So even though their OS still ships with these scripts, if you try to run these scripts, they're going to fail. And it's going to say, oh, System Integrity Protection is on. You have to turn this off if you want this script to execute. And you can turn System Integrity Protection on if you reboot into the recovery mode and toggle it. But that's going to work, for example, on your own developer box if you're poking around. But if you want to utilize dtrace, for example, in a security tool, that's not going to work for end users, because they're obviously going to have system integrity turned on, and they're not going to want to jump through the hoops of turning it off. So finally, we have OpenBSM. And OpenBSM, as I mentioned, is the de facto auditing mechanism on modern versions of macOS. Interestingly, it originally was developed on Solaris and then was ported to macOS by McAfee. Apple apparently had a contract with McAfee to do that. And on the slide, we can see kind of a conceptual overview of how OpenBSM auditing works. So in the kernel, there's going to be some auditable event, for example, a new process that's created. This will get noted by the OpenBSM subsystem. It'll then be added to a kernel queue and then committed to user mode, either by writing to the OpenBSM audit log file or to the user mode audit pipe. So let's take a closer look at this briefly. Again, we have the syscall interface that we talked about before. And in this, there's also some code to generate OpenBSM auditing events. So for example, we can see there's a call to audit_syscall enter. And then after the syscall has occurred, there's a call to audit_syscall_exit. And again, these are OpenBSM macros in the kernel that will generate audit events. So Jonathan's book kind of goes into the technical details of all of this. But basically, what these macros do is they generate audit events and then propagate that out to user mode, either by writing to the log file or to the audit pipe. So one of the cool things about OpenBSM is you can configure it with a variety of files. And what the configuration files allow you to do is specify to the kernel what events are of interest to you. So interestingly, this is actually enabled by default on macOS. And if we look at, for example, the audit control file, which is in /etc/security, we can see there's these flag parameters that have a variety of values, specifically LO and AA. We can look at another file, the audit classes, to kind of decode what these are. So we can see that LO maps to login, logout, AA to authentication and authorization. So what this basically means is the kernel is going to be auditing login and logout events and also authentication and authorization events. But no other audit mechanisms, audit events are going to be recorded unless you modify these flags. So for example, if you want to audit file events, you basically just go in and edit these flags. All right, let's briefly talk about the audit logs. They're basically stored in /var/audit, and there's several files. Basically, once a file max is hit, what happens is the kernel just creates a new file. And you can always tell what the current one is because it's going to be symlinked to one that ends in not underscore terminated. Now, if you dump the data in these OpenBSM audit log files, you'll see that the data is in a binary compressed proprietary format. Luckily, though, there's utilities we can use, such as Apple's PR audit, and this will decode the data for that. So if I, for example, generate a login event by executing sudo and then some user, and then when I'm done, type exit to basically exit that session. If I then go and examine the current OpenBSM audit log file, I can see that both a user authentication event and a logout event has been recorded by the operating system. Okay, so that wraps up our tour of auditing capabilities of macOS. Now the question is, what of these mechanisms should we use? Either to perform continual auditing, perhaps for incident response, or, most importantly to me, programmatically in security tools. So FS events is pretty good, but the main limitation is it can only record file I/O events. So that's a pretty big limitation. If we, for example, want to monitor process events or network I/O events, we can't use the FS events APIs. Kdebug is really powerful, but there's one main problem with it, and that is there can only be one consumer at a time. So if you write a security tool and you're using the kdebug auditing mechanism, and then the user, for example, wants to use FS usage, which is Apple's built-in file monitor that ships with macOS, FS usage won't work anymore and will throw an error message saying, hey, someone's already using kdebug event. So this is not really something you want to cause users. So again, it's not maybe the ideal mechanism to use. Dtrace, again, is a great mechanism, but because it's not compatible with system integrity protection, again, it doesn't make sense to put into a security tool that you're going to deploy to a lot of machines. So this leaves us with OpenBSM, which kind of checks off all our boxes. It's compatible with system integrity protection and gives us access to all the events of interest. It also has a nice programmatic API, and there can be multiple consumers. So now let's talk about how to leverage OpenBSM programmatically in Mac security tools. So one of my side hobbies is to create a lot of open source Mac security tools, and these tools need to perform things like tracking file I/O, monitoring for new process creations, and a lot more. You can also imagine perhaps you want to create more traditional AV tools or malware analysis tools, for example, a file mon or a process mon that can use these auditing mechanisms. So I used to use dtrace programmatically, but as I mentioned, due to system integrity protection, it's essentially dead. Luckily, though, we have OpenBSM. So programmatically, how does one utilize or make use of OpenBSM in code, for example, in a monitoring utility? Now, we'll dive into each of these steps, but conceptually, from a high level, it's pretty easy. First, you connect to the user mode audit pipe. You then specify what audit events are of interest to you. For example, you can say, I want file events and process notifications. And then you basically read off this pipe, and the kernel will deliver to you audit events. So pretty standard. So I mentioned step one is to connect to the user mode OpenBSM audit pipe. So in code, as root, you just call fopen on this pipe, and it's at /dev/audit pipe. And then as audit events are captured, they will be written out to this pipe from kernel mode. So now we've opened this pipe, we need to specify, as I mentioned, what audit events are of interest to us. So here, for example, let's build a simple process monitor. So we're going to say, OK, we're interested only in process events. So we can go into the audit_class file and look up what OpenBSM audit events relate to process creation, process events. And we can see there's two. There's PC and exec. So in code, what we do is we basically send an ioctl to the kernel saying, hey, these are the OpenBSM auditing events that are of interest to us. Now we've opened the pipe and configured it. We can start reading off it. And since we've configured it, anytime now there's a process event, the kernel will deliver that to this pipe, and we can consume off that. So if we look for the documentation, you can see there is a OpenBSM API called au_read rec for record. And it basically takes in the file descriptor to the audit pipe and a buffer for the record. Now, the documentation says it returns 0 on success, but that is not true. It actually returns the number of bytes it has read. So the documentation is incorrect. So now we have an audit record that we have read off the audit pipe. And Apple calls this a token record. We have to parse this in order to consume it or utilize it in our tool. So what we do is we invoke the au-fetch-toke method to tokenize the audit record. And this will split it into a variety of toke-stir structures. Now, each of these structures contains some important members. The first is the ID or type. This allows us to identify the type of structure it is. And all these structures are listed in the lib.bsm.h file, which ships with macOS. So some notable token types include a header and a trailer, which obviously start and end a record. And then there'll be other token types that correspond to the event. So for example, for a process creation event, there will be a record that corresponds to the path of the process that is created. There'll be another one for the process arguments, process parents, et cetera, et cetera. So what we do to process these tokens, we just switch on the token type, again, to determine the type of token that we have. And then we have token-specific logic to pull out the information that's of interest. So for example, I mentioned there's going to be a path. So what we can do is when we see the token that's associated with the path, we can record this path, for example, convert it into an NS-string object, and then consume that in our tool. So if we put this all together, we now have a nice process monitoring library. This library is open source, it's available on GitHub, and it's called procinfo. The cool thing about it is it's very easy to use. You basically link in the library, and then what you do is you create a block of code that you want the library to invoke anytime there's either a process creation or process termination event. And then you basically allocate a process monitor object and then invoke the start method passing in the block. The library takes care of everything else, all the auditing, configuration, the tracking of process events, parsing all the tokens, et cetera, et cetera. And then it will invoke this block of code whenever there's a process event. And it also does other cool things like generate the signing information of the process that's being created, extracts the ancestors, et cetera, et cetera. So very easily now, whenever a new process is created, you can see who created it and also the signing information. So you can say, oh, this is a trusted Apple process, this is something from the Mac App Store, or this is unsigned. That's odd. Okay, so that was an overview of auditing mechanisms and how to utilize OpenBSM programmatically in security tools. Now, since this is kind of a technical hacker conference, let's now talk about some more interesting, at least to me, topics. So time to put on our hacker hats, either gray, white, or black. You know, we're not going to discriminate here. And we'll talk about some kernel bugs that existed in Apple's OpenBSM kernel-mode code. So the first bug we're going to talk about is a kernel panic. And I kind of like this bug because I found it totally by accident. And I always kind of have this joke that like finding bugs on macOS is so easy that like if you're writing security tools or just splunking around, like you're going to inadvertently come across a lot of really interesting bugs. So I had this process info library I'd written. Again, it utilized the OpenBSM auditing subsystem to generate process events. Again, I mentioned that I have a variety of security tools, for example, one that generically detects ransomware. And one of the capabilities of this tool is it needs to track processes so that when a certain process creates files, it knows what process that is, who spawned it, et cetera, to basically classify that process. So I swapped in my procinfo OpenBSM auditing process monitoring library, ran the tool, went off to lunch, and a few hours later came back and my box had panicked. I was like, okay, it's kind of annoying, like maybe there's some faulty hardware. But started the tool again and came back the next morning. Again, my box had panicked. And again, first I was a little annoyed, but I said, oh, hey, now we have a repeatable kernel panic on the most recent version of macOS. Like, that's kind of cool. So what let's do now is walk through that kernel panic to find out the underlying cause of the bug. So the first thing we're going to do is we're going to start with the kernel panic report. And kernel panic reports are great because, as we'll see, they have all the information that you need, generally speaking, to track down the underlying cause of the bug. So if we look at this, there's a lot of information, but I've highlighted in green kind of the pieces of information that are valuable to us. So first we see there's something that says type 14 equals page fault. This indicates why the kernel panicked. It's basically said there's a page fault, which means there was an invalid read or write, likely to an unmapped page. Next we have RIP, which is the 64-bit instruction pointer. And this has the address of the faulting instruction. So this is the line of code, or the address of the opcodes that were being executed when the kernel panic occurred. Finally, we have fault CR2. This has the actual address that the kernel was trying to reference that triggered the page fault. And then at the very bottom, we have the kernel slide, which is just the amount in memory the kernel was slid due to address space layout randomization. So as I mentioned, the goal is to figure out why this panic occurred. So since we have the address of the faulting instruction from the kernel panic report, what we can do is we can disassemble the kernel and go to that address in the disassembly. So we load up the kernel in IDA Pro. And the first thing we have to do is we have to rebase the file image so that it maps the in-memory image. Because again, when the kernel is loaded, it gets slid in memory because of KASLR. So once we rebase the kernel, we have the address from RIP in the kernel panic report. We put that in the jump to address pop-up in IDA, and we hit G. And what we do is we land at a compare instruction in the audit arg sock adder function. This is an Open BSM audit function, which makes sense because, again, my utility, user mode utility, that triggered the kernel panic was utilizing the Open BSM auditing. So basically, this now indicates that in user mode, if you were talking to the APIs, there was some bug in the kernel that would trigger and crash the box. And we can see it's a compare instruction that's doing a compare of RBX plus R13 plus 2. And it's basically checking if that address is 0. Now, luckily, the audit arg sock adder function, which we'll be talking about a lot, is open source. So we can browse to opensource.apple.com and look at the source code for us. So the goal is to figure out what line in this source code maps to the compare instruction. Again, the compare instruction we got from disassembling the kernel. So if we look at the kernel code, we can see that when bind is called on a socket, it invokes the audit arg macro to audit the socket event. Basically says, OK, binding a socket is an event that might have security implications, so I'm going to audit this event. So in turn, it calls this audit arg sock adder function, which, among other things, determines what the type of socket is creating. So we can see there's a case for Unix sockets, AF_Unix. And what we can see is at the bottom of the slide, there is some code that's checking to make sure that the path of the Unix socket is null terminated. So if we look at the source code, we can see that this basically maps to our compare instruction. So the question is, what are these register values? And more importantly, why does this comparison cause a kernel panic? So if we look closer at the audit arg sock adder function, we can see it locally declares a sock adder Unix structure for a Unix socket. And if we look at the definition of this structure, it's in the un.h file, we can see that there's a length, a family, and then a path. So if we go back to the code for these Unix socket, we can see that it basically assigns a passed-in sock adder structure to the Unix sock adder structure and then calculates a length. Now, if we go back to the compare instruction, we can now understand the values of each of these arguments. So for example, the RBX register at the time of the crash is a pointer to the Unix sock adder structure. R13 is the length minus 2. And then there's a plus 2 because the offset of the path starts at plus 2 within the socket structure. So since the kernel panic report contains all the register values at the time of the crash, we can basically plug in the values and basically recompute the address it was doing the compare instruction. So we basically go to the crash report, pull out RBX, R13, and add 2. And what we do is when we compute that address, we get something that ends in 4F000. And two observations about that. First, that matches the fault CR2 address, which indicates, yes, this was the address that caused the kernel to panic. And also, since it ends in 000, this indicates it's at the very start of a new page. So here's a diagram of exactly what was happening to cause the kernel panic. So basically, we have this Unix structure that was size 16 or 10 in hex. It was allocated at the very end of a memory page. So basically, memory page, the last thing it had was this Unix socket structure. What happened was the compare instruction came along, and since it's trying to check if the path in the Unix socket is null terminated, it goes to what it thinks is the end of that structure, but it actually goes 1 byte past that and tries to read that byte. And since the very next byte after the path is an unmapped page in kernel memory, when the instruction tries to access that, that's obviously going to cause a kernel panic. So I was intrigued. I was like, okay, I understand, why this bug is occurring, but why is there this off by 1 read error? So if you read a little more about Unix sockets, you find out that this path does not have to be null terminated, which is why Apple is checking to see if it is null terminated. But there's all this confusion online about how to check this path. And the funniest is, if you actually look at the source code in the Linux kernel, they have an intentional off by 1, where they actually go 1 byte past the end of the path and check if that is a 0 there. However, the comments in the code say this is intentional and this is okay because we guarantee that the very next byte after the end of the path is always going to be mapped in, so this is never going to panic the box. However, that same assumption does not hold true on macOS. So when you get a structure that's allocated at the very end of a page with the adjacent page being unmapped, this causes a kernel panic. So kind of an interesting bug. All right, so that was a kernel panic. Kind of lame. I mean, it crashes the box. It's just a read. It's not exploitable. So let's talk about some real kernel bugs now. So the first thing I reported this bug to Apple. I said, hey guys, here's a scenario where user mode code can trigger a kernel panic if a Unix socket is being audited and the structure happens to align right with the end of an unmapped page. And they said, okay, cool. We'll fix that. They silently patched it, so there's no CVE associated with this. But if we look at the patch, we can see that the way they decided to fix this was by using a strl copy. Now, as their comment notes, they say make sure the path is null terminated. And if you're familiar with strl copy, it's basically a safe str copy, which means it'll never overflow the buffer, but it will keep copying until it finds a null termination. But again, this path is not necessarily null terminated. So more specifically, strl copy is, as I mentioned, going to copy until it fills up the buffer or until it hits a null or 0. So if our socket is smaller than the buffer and we create a socket that isn't null terminated, we can potentially leak random kernel memory data. So let's take a closer look at this. First, we have some code that creates a Unix socket. And if we look at the kernel, we see that this is going to call first, when we call bind on this, it's going to call something that's a method or a function called get_s. And what this function does is it's going to zero out a structure, and then it's going to copy in that socket structure that we're trying to audit. So basically, it's copying it in from user mode to kernel mode. And it copies this in via the copy-in method, which just copies in some specified number of bytes. So now let's try to create a Unix socket that is not null terminated. Because again, we want to basically get the vulnerable strl copy to be called on a string that's not null terminated, so then it starts copying random kernel memory into user mode. So as I mentioned, the way they copy in the path is they first zero out the structure and then copy that in. So since they zero out the structure, we have to create a path that fully fills up that structure, because otherwise it'll be inadvertently null terminated because they first zero out that structure. So if we look at the size of this structure, we can see it has a max size of 128. So what we do in user mode is we simply allocate 128 bytes. We fill that with 41, 41, 41, and then we basically set the length to max and the family to Unix socket. We then call bind, which will trigger the audit event of the socket. And what we can do is we can see we have the socket structure on the slide. So again, we can see it's 128 bytes, it's a Unix socket, and it's filled with 41s. Most important thing, though, is it's not null terminated. So there's no zeros in this structure. If we then call bind, this is going to trigger the vulnerable stir L copy in kernel mode. And what it's going to do now, it's going to start copying bytes from our non-null terminated path. So here's a diagram of that. And we can see if we have the structure in memory, if after the structure there's a 1, 2, 3, 4, 5, 6, some number of bytes, the stir L copy is just going to start copying all those bytes and then write that out to user mode, either to the audit log file or to the audit pipe. And again, obviously, if there's sensitive information in the kernel, hashes, tokens, and et cetera, this will all get leaked. And again, this was Apple's fix to a kernel panic report. So that's kind of the funniest thing of this all. So let's briefly walk through this in a debugger to show this kind of happening in action. So the first thing we do is we set a conditional breakpoint on bind. And then here's our user mode code to create this null non-terminated Unix socket. We then call bind in user mode. This will trigger our kernel mode breakpoint to be hit. And then if we dump various values, we can see, okay, yes, this is our kernel, this is our Unix socket, and yes, it has a path that's not null terminated. So if we then set a breakpoint on the vulnerable code, we can hit continue in the debugger, and then it'll break as it's about to audit this Unix socket. So at that point, we can look at the registers, and we have a table on the slide, which is the mapping of what the registers contain at the vulnerable stir L copy. For example, we can see that RAX points to the index of the byte to copy. RBX plus 2 is the source bytes, which is the path. And then RBP minus 130 is the buffer it's going to copy it into. So if we step over this, we can see that it returns 127, which means it's copied 127 bytes. So why 127? So recall we're copying from a Unix sock adder structure, and we've set its size to 128. Now the path starts at offset 2, which means that the maximum path length is 126. In memory, if we dump the path that we're about to audit, we can see that right after it, there's a random D7 and then a random 00. So what happens is the code has gone through, copied to the end of the path. Since the path isn't null terminated, it then copied the next byte, which happened to be a random D7, looked at the next byte that happened to be 0, so stopped copying. So in this case, we've leaked 1 byte. Now, you probably want to leak more than 1 byte at a time. And it turns out you can. So if you create a socket that's bigger than 128, instead of getting allocated on the kernel stack, it gets allocated on the kernel heap. So then you create this socket, and again, just call bind on it, and the vulnerable stir L copy will just start copying random kernel bytes until it hits a 0. So you can change the size of the socket. You can call this as many times. There's no side effect of this. But every time you do this, you will leak more and more kernel memory into user mode. OK, so we've talked about kernel panic and a kernel information leak. But I still wanted something a little better. So if we look within the same audit arg sock adder function, we can see that there is an interesting B copy. And a B copy is just a mem copy. It's basically copying something from a source buffer to a destination buffer and some number of bytes. Now, anytime you see a B copy function, if it uses the source buffer as the number of bytes to copy, take a very close look at that. Because if the destination buffer is smaller than the source buffer, you may get a heap overflow. So what bcopy is doing, it's basically just copying a socket into a sock adder structure. So if we look at the table on the slide, these are exactly what it's copying. So the source is just a sock adder structure. The destination is a sock adder storage, which we'll look at that closer. And the size is the length of the source buffer. So the question then comes is, can we basically create a source sock adder structure that's bigger than this destination buffer? And the answer is yeah. So the destination buffer is always going to be 128 bytes in size. So if we can create a socket that has more than 128 bytes, we will get a nice ring 0 heap overflow. So again, we're going to use a Unix socket because a Unix socket allows you to specify a path. And the path can be bigger than 128. So this allows us to create a socket that's essentially bigger than the destination buffer. So we create the socket, and then we call bind. The call to bind will trigger the vulnerable audit code, which is trying to audit the socket. And then this will invoke the vulnerable B copy. So the diagram on the slide, we can see we have this Unix socket. I've created it to be 200 bytes in size. It could be bigger, it could be smaller. But the important thing is it's bigger than 128. So the B copy comes along and says, OK, I want to make a copy of this path. I want to make a copy of this socket structure. I'm going to basically copy it into this destination buffer that's 128 bytes in size. And the length I'm going to use is the size of the source buffer, not the size of the destination. So since the source buffer is bigger than the destination buffer, we get a nice heap overflow. So how do you exploit this vulnerability? Due to time constraints, can't really go into all the details, but it's actually pretty easy for a variety of reasons. So first, we control the number of bytes to copy. So it's a tactical overflow. You can copy and overflow as many or as few bytes as you want. We also control the values of the bytes being copied. So they can have zeros, they can have 7Fs, they can have, there's no constraints on that. Most importantly, though, if we look at where this destination buffer is that's getting overflowed, we can see that it's part of a larger structure. So it's self-contained with something within another structure. And this is important because this means that after that buffer, there are always going to be other values, for example, pointers, that we can corrupt. So normally when you're exploiting a heap overflow, you don't know what's going to be next to the buffer you're overflowing. So what you have to do is you have to spray, you have to allocate, you have to groom the kernel heap. Then you have to try to get an adjacent object that you control, trigger the overflow, and then gain code execution that way. In this case, though, we have a self-contained overflow. And again, the destination buffer is part of another structure, so there's pointers there that we can tactically hit. We always know those pointers are going to be there. So here, for example, we can corrupt some of those pointers and set them to 41, 41, 41, 41. So once you have this ability, there's some other talks that have been presented about exactly how to leverage this to get control of the instruction pointer and then do all sorts of evil things. For example, disabling system integrity protection, gaining unsigned code execution in the context of the kernel, all that good stuff. All right, so let's wrap this all up. So we started by talking about the many benefits of auditing. So again, if you're interested in doing malware analysis or writing security tools for macOS, definitely check out the auditing mechanisms. You can utilize them to create very powerful auditing tools pretty easily. We talked about a kernel panic that was inadvertently found by a user mode process monitoring library. That was silently patched in the 10.12.4.beta. When I looked at Apple's patch, I saw that not only had they not patched the bug, they actually had introduced an even worse vulnerability. So a little secret, look at Apple's patches because they mess them up all the time. So you can find some really interesting bugs. Basically just wait till they release some CVE details, diff the kernel, look at their patches, and free O-days. And then finally, we also showed a heap overflow that would give us code execution in the context of the kernel, allowing us to do things like bypass system integrity protection or execute unsigned code in the context of the kernel. So very briefly, since you're attending my talk on Mac security, I just want to briefly mention my personal Mac security website. A lot of free open source Mac security tools. I also blog about Mac malware and blog about 0 days and vulnerabilities I find. So everything here is free, so hope this doesn't sound like a sales pitch. All right, so that's a wrap. Again, I'm on Twitter, Patrick Wardle. The website is Objective-C. And I think we have a few minutes for questions. If not, I will be around after the talk. I would love to chat. Again, thank you so much for attending my talk. I really appreciate it. Yes, question.
I missed something. The heap overflow you explained at the end. Is it related to the same flow that's linked to the kernel?
Yes, so the question was the heap overflow related to the same control flow, the same auditing mechanisms? And the answer is yes. So all three bugs I talked about were all within the Open BSM code, which lives in the kernel, the auditing code. And actually, all three bugs were in the same function. So there's a lot of other auditing functions that you might want to take a look at. I don't think anyone's audited the audit code. But again, yes, so basically, to answer your question, it was all within the auditing subsystem. First, the panic was triggered inadvertently when I just started using it, and then I took a closer look, audited some of the code, and found the kernel information leak due to Apple's patch, and then the heap overflow was just actually 3 lines of code above. So I would audit that code. There might be some other interesting bugs there. Yes, question? So the first one was, okay, so the first panic, and I was like, this is annoying. And I was like, oh, cool, this is like a security bug. And then I decided to look at Apple's fix because I wanted to make sure that when I deployed my tool, my user mode tool, it wasn't going to cause users' computers to panic. And then I looked at their fix, and I was like, what were they thinking? Like, they say it's not null terminated, and they use a strl copy. And then the function was 20 lines of code, and I was like, okay, there's already 2 bugs in here. There might be something else. And when I was testing the kernel information leak, it actually triggered the heap overflow. So again, like finding kernel bugs in Apple is, it's still pretty easy. So, or maybe I'm just really lucky. But no, it's easy. Awesome. Well, thanks again for attending, and I'll be around if you want to chat. Also, these slides I will be online, I think, tomorrow. So thanks again.